Okay, Assalamualaikum everyone. Selamat sejahtera. Okay, so today I would like to present the stars, okay, the new topics. We continue from the previous sun, then we continue to the next chapter, which is the stars. Okay, so what we have to learn in this topic. Okay, so these are the sub content. So the solar neighborhood, the luminosity, the stellar temperature, stellar size, okay, HR diagram, extending cosmic distance scale, stellar masses, and also the other stellar properties. Okay, so let's see. What is the solar neighborhood? So our galaxy contains more than 100 billion of stars, and which we have the all orbiting in the galactic center, which is 25,000 light years away. So the essential properties of stars, which are the appearance, the birth, the life, death, interaction, can be understood in terms of basic physical stellar quantities, which is the luminosity or the brightness, temperature, chemical composition. And I want you to fill up these two essential properties, okay? Which is the size and also mass here. Okay, these are the two example. Okay, so let's see the stellar parallax. Okay, so stellar parallax in astronomy, astronomers use the parallax to measure the distance of two stars by observing a star from two different points on the Earth's orbit. Okay, so they can calculate the angle of the parallax shift. So this angle is then used to determine the distance to a star, as you can see here. So, okay, these are the photograph of the some of the baseline and to measure the angle. Okay. Next. So by comparing the observation of a star at different times of the year, we have extended our baseline to 2 AU. Okay, so the diameter of the Earth's orbit. So the image here, you can see in the right side here, is the diagram that shows how astronomers use the parallax to measure the distance to stars. So we have a background star, stars, the parallax angle, the Earth's orbit, okay, and also the sun and also the baseline. So the baseline here is the distance between the Earth's two position in its orbit. Okay, where the background star here is the distant star that I use as a reference point. Okay, so these are the formula that related to the distance is called a parsecond, or the parallax in arcsecond, or this the unit is PC, so it can be related to a star's parallax. So these are the formula. Okay, so our nearest neighbors, so the closest star to Earth is called the Proxima Centauri. So it's a triple star system that known as the Alpha Centauri complex. Okay. And also we do have the next nearest neighborhood to the sun that beyond the Alpha Centauri system, so-called the Barnard's star. Okay, so this is a diagram that showing the distance in parsecond, okay, which the sun in the middle and all the stars, the brightest stars and all the main stars related to be here. Okay, so our nearest neighborhoods is an adaptive optic system, and we can measure the stellar parallax as low as 0.03 or 30 PC. Okay, so the Hipparchus satellite extend the range of accurately measured the parallax to 490 BC. Okay, so for ESA, Gaia, it's launched in 2013, measured up to 10 kilo BC. So there are two components of stellar motion, okay, which radial velocity and the transverse velocity. So we can read here the differentiation between these two stellar motion. Okay, and we have the proper motion, which is the parallax corrected annual movement of star as seen from the Earth, and it can describe the transverse velocity of star relative to the Sun, and also is measured in terms of angular displacement or the arcsecond per year. Okay, these are the Barnard star. Okay, Barnard star has the largest known proper motion. Okay, it has moved 228 in 22 years. Okay, so at the distance of Barnard star, angle of 10.4 correspond to a physical displacement. Okay, that traveling for a year. So that's mean is that its a transverse velocity is 89 kilometer per second. So this Barnard star is substantial proper motion as a result of its close proximity to the Earth. Okay, and its high velocity relative to our Sun. Okay, so now is the Alpha Centauri. Okay, and the radial velocity is measured through a Doppler shift, Doppler effect. So as you can see here, okay, so basically, astronomers rely on the advance of astrometric observation, okay, and simulation to determine the future position of stars with a greater precision. Okay, so for this one is using a theory of Pythagoras. Okay, it's through spatial motion, and it will get the estimation lah, the greater precision of estimation by using this technique. Okay, now is the luminosity and apparent brightness. So luminosity is intrinsic property of a star, does not depend on location or motion, and referred to as the star's absolute brightness. And then we have the apparent brightness, okay, the amount of energy that's striking a unit area of light sensitive device per unit type or charge coupled device, okay, CCD. And it also depends on our distance from the star. Okay, so we have another inverse square law. Moving outward, a star's radiation passes through imaginary spheres of increasing radius around the source. Okay, so for example here, the light source at the middle point. So all the light will moving outward lah, keluar daripada that particular source in the middle. So it coming to the number 1, number 2, and going to yang paling luar sekali. Okay, so the star luminosity is constant. The farther the light travel, the lesser energy will pass through each unit of area. So basically, the brightness is inversely proportional to the square of distance from the star, which is the 4 pi r squared. Okay. So the luminosity is proportional to the energy, which is the apparent brightness, and crossing any spherical shell surrounding the star. So therefore, we get following relationship: apparent brightness with luminosity and the square of distance. So it's mean a two identical star can have the same apparent brightness if they lie at the same distance from the Earth. Okay, so in other words, a bright star is either very luminous or very near to Earth. So to determine the star's luminosity, we must do these three, which is determine the star's apparent brightness, measure the star's distance, and use the inverse square law. So these three important things to do to determine the luminosity of star. And then the magnitude scale, okay. Magnitude scale is the instead of using SI unit watt per meter squared, okay, apparent brightness is more convenient to be measured using magnitude scale. Okay, so this introduced by Greek astronomer Hipparchus. So Hipparchus classified with naked eye, okay, into 6 groups. And then when going through the advancement, we have the telescopic equipment later, and it will improve the technique of classification. So the modern technique is use this. Okay, these are the timeline, yeah, they put your timeline with the advancement. Okay, and then we do have the brightness ratio here to relate the different in magnitude. Okay, and also for F2 and F1, the ratio of the brightness. Okay. So in order to compare the intrinsic brightness of star, we measure a star's absolute magnitude, which is apparent magnitude. Okay, with this distance from the observer. So using the magnitude scale relationship, we have this brightness, flux F, the L, and also D. Okay, the relation here. So the sun's absolute magnitude is 4.83, and difference M minus M capital is measurement of a distance modulus of the micro. So now is the stellar temperature. Okay, so stellar temperature in the constellation Orion. Okay, the colors of the red star is Betelgeuse and the blue star Rigel are clearly evident. So these colors are intrinsic property of star together with their brightness and black body curve. So we can determine their surface temperature to be 3200 and 11,000 Kelvin. So by using the telescope filters, we can have a basic shape of black body curve, which is a very well understood star's temperature. And we have this B filter, V filter, and U filter. Okay, for visual, green to yellow, and also UV lah. Okay, infrared. Okay, so here you can see the B and V filters. Okay, emit the different amount of light for object, okay, at different temperature. So you can see curve A is for 30,000 Kelvin here, 10,000 and 3,000. So for different curve, different temperature. So the entire blackbody curve of a star can be reconstructed on the basis of only those two measurements. So for non-spectral light analysis using a standard set of filters is known as photometry. Okay, so you can see the color and temperature information of stellar colors here. And stellar spectra to classify the stellar properties. Okay, the additional knowledge of stellar physics obtained through this spectroscopy. Okay, so when we talk about the spectroscopy, so it's related to, it must always come with absorption, like with different temperature lah, as you can see this diagram here, from 3,000 up to 30,000 Kelvin. So you can see the different in the absorption line and the material, iron, calcium, and we have oxygen. For hydrogen is 30,000 Kelvin. Okay, for spectra with more than 25,000 Kelvin will show the strong absorption line, ionized helium and multiple ionized and tightly bound elements, which is these three: oxygen, nitrogen, and silicon. So for hydrogen lines, is strongest in star with temperature about 10,000. Okay, so this one is for calcium, example of calcium and titanium, and also for approximately 4,000 is hydrogen lines. Okay, this spectral classification. Okay, so to classify a star by its surface temperature, so astronomers will will categorize this on alphabet, okay, into a new sequence based on the temperature. And the hottest star are designed by this. So the hydrogen lines is the very weak spectrum, and come to yang paling daripada yang weak, very weak to the strongest one lah. Okay, so this stellar designation called as the spectral classes. Okay, so this is how they you can memorize. So this is a spectral classification with the different spectral class and the temperature. Okay, so for stellar size is a direct and indirect measurement. So the size of big, bright, and close enough star can be measured directly. Okay, so for example, here you have the Betelgeuse. Betelgeuse is very large enough to be resolved by HST, Hubble Space Telescope in the UV. Okay, and using the long baseline interferometer. For angular size and distance is unknown, and radius can be measured by simple geometry. Okay, so this one is for Stefan Boltzmann law. So you can see the relationship between luminosity, area, temperature, and also radius. Okay. Okay, these are the three constants for luminosity, radii, and solar temperature. You can see the properties here. For blue, red giant, and the red dwarf. How these three parameters is vary with coming from the blue, red, and also the red dwarf. Okay, these are the relationship. We can write the equation for L equals to R squared T power of 4. So this is the relation here. So to estimate the stellar radii, we have this configuration 80, for 80, 75, and 90% for different star. Okay. Okay, maybe one of the example I can mention here for Aldebaran. Okay, which surface temperature about this value and luminosity, and also imply it has a radius. So you can see for different type of a stellar size. Okay. Okay, so when you want to see the clear picture, maybe to summarize all this, so this is the diagram. Okay, so you can differentiate the radius, the size, and the size of a different star mentioned. Okay. Okay, now is coming into the HR diagram, the Hertzsprung-Russell diagram. Okay, so what is the Hertzsprung-Russell Russell diagram? Okay, this is from slide 34. Okay. So as you can see, the HR diagram shows the luminosity, okay, versus the temperature, and name after these astronomers, and also known as the color magnitude diagram. Okay, vertical axis shows the luminosity, okay, and the absolute magnitude. So the horizontal axis shows the surface temperature, okay, with the BV color index. So their work in 90s, okay, laid the foundation for our understanding of this stellar evolution. So this HR diagram in their independent studies, okay, plotted a stars based on their brightness and also temperature. So the temperature is referred to the spectral class. So this resulted in the creation on this diagram, okay, which is a fundamental tool in stellar astronomy. Okay, so this is stellar radii. Okay, it's varied along the main sequence. So the diagonal dashed line in the figure represent the constant stellar radii. So thus we have radius L and T. Relationship is clear with a single plot. And stars with a great apparent brightness are mostly blue and blue giant and blue supergiant. Okay, so for main sequence, you can see here the content of what is the main sequence. The white dwarf region that lies at the bottom here. Okay, what for red giant region is the upper right corner. So many of the brightest stars seen in the sky are red and not found within the 5 PC of the sun. Okay, so 90% of all stars in our solar neighborhood are the main sequence, as you can see here, the curve of the main sequence. So this HR diagram allows us to find independent measure of the luminosity without knowing the distance. Okay. So this process using a stellar spectra to infer the distance, so-called the spectroscopic parallax. Okay. So this the diagram for spectroscopic parallax that can measure can be used to determine the method that actually utilize the relationship between a star spectral type and also the luminosity, okay, by analyzing a star spectrum. So astronomers can determine its spectral type, okay, using the information of data from nearby star with known distance. The distance must be known lah, so they can estimate the star's intrinsic luminosity. Okay, so this is the spectral line width and also information provided with the density. Okay, so this classification of spectral line width is known as the luminosity class. Okay. For example, the luminosity class of the sun, we have this G2V, Rigel, the blue supergiant, Barnard star, red dwarf, and Betelgeuse is a red supergiant. Okay. So yeah, we do have to include the Newton's law, which is a star's mass can be measured by observing its gravitational influence on a nearby star or planet using Newton's law. And most stars are members of a multiple star system, from which a majority of them are found in the binary star system, which is ada dua dia the motion dia tu dia sentiasa bergerak by dual lah, binary. So it consists of two stars in its orbit, okay, that held together by their mutual gravitational attraction. For example, we have the visual binaries, okay, the Kruger 60 that have widely separated members, bright enough to be observed and monitored separately. So spectroscopic binaries, okay, are more common. Okay, there are two distance to be resolved into a separate star. Okay, and by monitoring on Doppler shift of their spectral line, and a double line spectroscopic binary shows two distinct set of spectral lines. For a single line, it's a more common and shows only one line. So that is referred to the number of lines. And then we have these eclipsing binaries, quite rare. So the orbital plane of the star is also almost etched onto our line of sight. So you can see the intensity with the time. Okay, when you have this, it's not overlap, then the intensity is maximum. Where it's overlap, you can see it will straightly going down. Okay, will give you a minimal intensity. Okay, so this predict decrease in the starlight as one star transit, and the other is recorded as a light curve. Okay, and then I think this last part for stellar. So it's a stellar masses. Stellar masses is a mass determination of the orbital period with P. Okay, it can be measured by watching the stars orbit one another or by the back and forth velocity. So for example, A here, orbital semi-major axis can be obtained by direct observation of the orbit using the Kepler's law to correct for inclination. So this is the relation of the P and A. You can use a modified version of Kepler's third law to calculate the sum of the masses of the two stars. And then the ratio of masses can be measured by finding the ratio of the speed using Doppler observation. This is the equation. M1 V1 equals to M2 V2. Okay. So for visual binary, we have visual binary and spectroscopic binary. So if the distance is known, so the semi-major axis can be determined by geometry. And if it is not possible to determine the semi-major axis and inclination directly, okay, between slow-moving binary H-on and a fast-moving binary seen almost face on. So for double line binary, the ratio of masses can be determined, but only lower limits of the individual masses can be obtained. Okay, so this one for single line. Okay, so we have double line binary, single line, and the ecliptic binary. So all of those here is the information for different M. You can see the percentage for this one. Okay, where you can see the difference in scatter plot of luminosity and the radius. Okay, this is the lifetime formula with mass and luminosity. Okay, and this information of the all those stars and the spectral type. Okay, so we have the OB type stars. We now observe are quite young, and the KM type star we have their proton reaction. Okay, that will shine on for at least 1 trillion years. Okay, so that's all for this topic of the stars. So you can see all the main thing here is the HR diagram and also the spectroscopic properties that we have just learned about that lead to the estimation of the distance of star. Okay, that's all. Thank you.